started. Okay, so I'll first start a little bit on the table, so this camera won't pick it up, but that's okay, it's just a recap of what we learned. So, what did we do so far? We learned, we have three really important matrices when we control, right? What are these three matrices?
Command tracking, dynamic stiffness, and robustness.
And robustness, right? Or robustness is a different word for parameter sensitivity. So we always, when we do these plots of command tracking and dynamic stiffness, we have to also think about robustness, right? So you think about feed forward or you think about decoupling, they only work as good as your parameters are, right? Okay. So, and if we look at these, what do you think, which one is the most important when we think about modeling and building our state feedback controller?
Command tracking.
You think command tracking, so that's what I think most of the people would ever say, right? We're most interested in what our commands will yield. But once we learn a certain trick, we should have thought maybe not really, right? What's the trick that showed us that command tracking is really not our state feedback controller?
Step feed forward.
Feed forward, correct. Command tracking we do via feed forward, right? If we have a feed forward, we should get the right results. Robustness, still an issue, absolutely. But robustness we take care of with what? With our state feedback controller, and it basically looks like determines anyways, right?
Yes.
So really this dynamic stiffness is what should be what you're looking at if you design your state feedback control. So you shape dynamic stiffness for disturbances, for robustness, for all of these things, and command tracking we try to use your feed forward. You automatically get good command tracking with that anyways, and there are other tricks like DQ for instance, where you can't really get wrong command tracking anymore because it's DC, right? So with some integration portion that you do for your dynamic stiffness, you already get correct command tracking. Okay, so there's other ways to get good command tracking, but really what our state feedback controller should do is dynamic stiffness. Because that really needs state feedback. It needs information about the disturbance, right? So dynamic stiffness really is very important for our controller design. Okay. What else did we learn? So we learned about feed forward, and we learned about observers, right? So observers basically, what do they provide for us? What's the up and down? And that would be basically what we see in our homework, but what do observers do for us?
We get a pure signal from the impure signal.
Yeah, so they basically give us cleaner signals, right? So they are like a filter, but without like leading properties, right? So they're basically a better filter. And if we have model information, we should always use this. It's a better filter. But what did we see in dynamic stiffness happening? Did you have an overlay plot with and without Millenberger style observer? Not yet? So what you should see though is depending on the bandwidth of that observer, and basically so there's two things, how do we choose our bandwidth? Maybe first of all, of the observer, how do we choose that?
Observer bandwidth.
Yeah, why don't we just use an infinite bandwidth for that? Or like really high ones? Because this is all math. We don't run into voltage issues, right? That's math, there's some energy involved. So we can choose any bandwidth we want. But why don't we do it? If the bandwidth is really high, how good is the filtering? There's almost no filtering if you have a lot of bandwidth, right?
Yeah.
So increasing the bandwidth makes our filter worse. But increasing the bandwidth, and that would have been something that you would have seen in your homework, increases the dynamic stiffness. And that's just because we observe a state, but above its bandwidth, the information is not perfect anymore, and we don't have as good information about the disturbance anymore, right? Because the disturbance really comes from our measurement, and if that doesn't go through anymore, the information of our disturbance is also lost. So the bandwidth also determines how much deterioration you get in your dynamic stiffness. And you will see this if you use a Bloomberg observer and you have low bandwidth, you will see that the dynamic stiffness drops a little bit. So it's basically weighing between dynamic stiffness and filtering properties. That's what you do with the observer bandwidth. Okay? And there's another thing an observer can do. It can estimate also disturbances itself, right? Because the output of the controller should be an estimate of your disturbances. Also, the parameter sensitivity is also involved, though, right? So if you have wrong parameters, it's not just the stiffness, it's not just the disturbance, it's also information that comes from your wrong model. Right, so if the model is wrong, the state feedback control in your observer actually has a signal. If your parameters are correct and your state feedback has an output in your observer, you have a disturbance. Okay? So with good parameters, you can actually use an observer also to estimate your disturbance. And you could use multiple observers. You could use one for just filtering. You could use another one with a really high bandwidth to observe your disturbance, and all of these things, right? You can also use them for different ideas. It doesn't have to be one. There's also some cases where we use cascaded observers. We didn't really get in this course to that because we can't teach you everything, but that's also something. Anyway, so that's about the observers, and then we had one more thing in the cascaded state for played around with the cascade state of the VDC link, right? And I wanted you to find out what state is a good idea here. I already talked to Gyanendra about this, but do any of you guys, what state did you use, or what would have you used for the outer control? What would have been the state that you want to control?
For the
I thought about VDC squared.
You thought about VDC squared? Why VDC squared?
That's from that's based on the power relations.
Yeah.
So 1/2C VDC square is the energy,
Yeah.
and the rate of change of energy would be the power to the capacitor.
Yeah.
And then we have the input-output relationship between the powers.
So very good. Actually, yeah, the energy on the capacitor is VDC squared times C over 2, right? So VDC squared is really the information of the energy. But some people would, and I see this very commonly, they put a square root on this, right? And then they get VDC. But what is the square root? It's not linear anymore, right? When you do a square root of a type signal, it becomes not linear. So you unnecessarily make your system a nonlinear system, which means that it's operator independent. Now you can't use all the analysis that you think you can for the linear analysis. They don't apply anymore. You have to do Taylor series expansion. You have to basically try command tracking dynamic stiffness at different operating points, and you will see that your system changes with the operating point. However, when you use VDC squared, it is still a linear system, and you can use all the stuff that we taught you. So why don't you just keep it a linear system before you get all into trouble, right? So keep it linear, use VDC squared. So in real life, you measure VDC and you just square it. It seems like you do something nonlinear, but actually for your system, that's the state that you need for a linear control. Okay? So that's a very good idea to use VDC squared. There's other ways of doing this. You could, for instance, read a paper by Christian Vandenbroek from the University of Aachen. And he has a different way to do this. He uses VDC, but he decoupled some other things. And then it turns out you can use it too, but it's a little more complicated. But you can use it too, just so you know. And here's some really cool other neat tricks. So I encourage you to have a look at his paper at some point when we get a little bit deeper into discrete control. Okay, so this was basically the recap of the homework, what you should have seen, and what we learned in the lessons 1 and 2. And today we want to look into basically the real world, because nobody builds analog controllers. I did this once. We had this huge breadboard and we would build the observers with actual analog circuits, and we would build all of this with resistors and capacitors. And if you want to change a gain somewhere, you have to get a resistor out, put a new one in. It's tedious, and it's like really, really bad in practice. Nobody wants to do this anymore. So what do we do nowadays? We measure signals, we sample them, they go into a microcontroller, the microcontroller does the math and puts a voltage on, right? So that's what we do nowadays. So it is analog to digital conversion involved, and everything happens in discrete time. So all the continuous stuff that we learn, it's still valuable and it's still great to know. And in some cases, you can basically, if you sample very, very fast in respect to your slow system, you can basically call it a quasi-continuous state. And then you can apply all of these ideas too. But if it's too close, the tau basically of your system to your sampling time, then you will see that your approaches won't work anymore. Okay? But this is something you have to experience yourself, so I want to teach you direct discrete modeling today. Okay? And the first thing you have to always have up in your head is that there's no integration model in discrete domain. It's unfortunate, but that's the way it is. So, where we do in continuous domain, this 1 over S, there's no such thing in discrete time. There's always sample relationship between two states. And this transfer function basically between two of them, or the sampling relationship, changes in different systems. So what people try to do is they use approximation models, like maybe you heard it, like forward Euler or Tustin, very, very often used. So they basically say, we can approximate this, and we assume that what happens in between is rectangular, or it's a triangle or something like that. But if it's not really a triangle or not really a perfect line, the integration won't be right. So they just assume they can use a certain equivalency for Tustin for the integration, and then it might look like get that right. Put that on the homework too. So they basically say, for instance, Tustin says that this would be ts by 2, 1 plus e to the minus 1 over 1 minus e to the minus 1. And they just use this to replace the 1 over s. Okay? So that's one way to do it, and a lot of people will do this, and it's good that you know that these are out there. And maybe at some point where the system is so hard to describe, and you're actually oversampling anyways, really highly, you might get an okay result with this anyways. So, because you will learn today that discrete math, if you do direct discrete modeling, is not always very easy. Okay?
What's the expression there? It's 1 plus z power minus.
Oh, it's ts over 2 times 1 plus z to the minus 1, sorry.
The keyword is just in
Over 1 plus z to the minus 1. But it will be in your homework.
Why they cancel?
Yeah, is
Oh, sorry.
minus
That was my bad. On the camera, the guys who see this at home, we have this in the homework. Unfortunately, I have to have the camera here in the beginning. Okay. So there's no integration model, and you will see that it always looks a little bit different. Okay. But before we get into this, I want to teach you guys a little bit more about root locus And now that I think of it, I should have actually started with the camera over there. Because we have to do this first. Could you move the camera over here so we can see the board?
Oh, there.
Yeah, just so that you can see the board and whatever I'm here, and we have to move it back and forth. Unfortunately, because we only have one camera.
Thank you.
Okay, so have you guys heard about root locus plots or pole zero plots yet? We talked about all of this in math and transfer function, but we also like to plot this in a complex domain. So this is the real portion. This is the imaginary portion. And a first order system, like for instance our current control, just the LR, has just one pole, right? Where's that pole situated here?
It's on negative side.
Negative, and what value? So 1 over
R by
Ls plus R.
it's minus R.
Yeah.
It is, so let's put out the L. 1 over S plus R over L, right?
Yeah.
So the pole is at minus R over L. So if we now look at, and if we want to evaluate this, so this is our H of J omega. If we want to evaluate this in the amplitude, in general what we do is, we do the multiplication of all the amplitudes of every zero. All the multiplication, J to N minus J. That's basically how we calculate the amplitude and the angle. Of this, and it's the same as we use here, indices. Just do it real quick. It's basically of the zeros minus the ones of the poles. So that's basically how we evaluate it for all. If we have multiple poles and we look at one frequency, we can evaluate the angle and the magnitude. But what does it look like geometrically? What is this, for instance? Now, in our first order system, we only have this, right? So we have only one pole and j omega minus that. So what is that here? How do we draw this?
It has a position based on its magnitude. That would be on the real axis, negative real axis.
Yeah, but how for different frequencies? How do we put like different omegas in here? Where's j omega? Where would it be? If I put in j omega, where is it?
Imaginary.
It's on the imaginary axis. And all of these values are actually in omega, in radians per second anyways. So if I use, for instance, 50 hertz, then I would be about at 2 pi 50 radians. This would be my j 2 pi 50, for instance. And now the angle would be this angle, and the magnitude would be this here. So that's the j omega minus p. Okay? So that's how you geometrically basically draw this. So if we think about this, and by the way, we call this, at least in Germany, we call always the first order system a PT1. And we talked about this before. P basically stands for a proportional transfer function. with a first order delay. Or just one pole, and that's how it basically looks like a pole zero plot. Okay, and so if we now think about this and we would want to draw this over time, right? What angle would we start with? Or what would be the amplitude at the beginning? Let's look at amplitude and an angle. What would the amplitude start with?
Amplitude of what?
If we now, okay, sorry, this is for 50 hertz, right? And this would be then for 100 hertz and so on. I go up. So basically what I do is I evaluate this with different angles and different amplitudes for different points, right? So what would it be at 0 hertz? We don't have 0 hertz, but very low.
It would be just the pole.
Right. So it would start by R over L. And the angle would start at 0. What would it be at infinite? I just go infinitely up. How big is the amplitude? Actually, this is poles 1 over that, right?
It should be
So
R.
it's actually L over R.
It should be just R, right?
So,
It should be just 1 by R. It should be 1 by R. And we cancel out.
Oh, the end. Right, we took it out. We took out here, right? Yeah. Right, so the whole thing here would have been times 1 over L. Yeah, you forgot that. You're absolutely right. So it would be L over R times 1 over L, so it's actually 1 over R. Correct. And this makes sense, right? For a DC signal, we put a voltage on, the L shouldn't matter, right? Okay, so we started at 1 over R. But what would it be at infinite? So if we think about this line going up and up and up. So what's the amplitude of the pole at infinite?
tends to 0.
Infinite. So 1 over infinite, that would be 0, right? So the end would be 0.
And angle
And what would be the angle if you just go up?
tends to pi.
90 degree.
That's around 90 degrees, right? So we know the angle will be minus 90 and it starts at 0. So, and at our break frequency, we know that it starts really to drop. At the break frequency, we also know it's at minus 45. Right? Where's minus 45 here? Where do we get exactly 45 degrees?
When omega is same as alpha.
Exactly. So where omega equals R by L, we have our break frequency, right? So we know exactly at R over L, we have our breaking point basically, and we have the minus 45. Okay? This is just a way to draw this, to make maybe a little bit more understand what does a pole do. Okay? And if we now look at a second order system, where you have complex conjugate poles, the whole thing looks a little bit different. So complex conjugate is always the same real portion, but plus minus the imaginary, right? And here, the angle is actually, to draw this imaginary line here, we have two angles like this. Theta 1 and theta 2. And the angle would be theta 1 plus theta 2. And yes, and basically, and both, this would be again the magnitudes, and you could multiply them with one another for this equation. Okay? So, what would that mean?
What is this plot?
Was what?
What is this plot?
This plot here?
Yeah.
Again, the same one, sorry. This is imaginary, this is real, and this is for a second order system. So our pole is basically a real portion plus minus an imaginary portion. So it very often happens if you have a second order system, you have a complex conjugate pair,
Yeah.
right? And the overall angle you can basically calculate like this, as we said, right? So they add up, and basically minus of that. And also the magnitude would be multiplied onward, as we have already shown at these. So if we think about this, what would that mean for the angle, for instance? The magnitude is a little harder. We just do the amplitude here, the angle. The angle of J of. Where does it start? So again, at 0 Hertz we start here, right? This is negative, this positive, this is the same, right? So at 0 Hertz we have zero angle, right? And if this goes up, this angle gets bigger plus, this gets bigger plus. What's at infinite? What's phi 1 and theta 1 and theta 2 at infinite?
Phi.
Right, so one would be pi over 2, the other one also pi over 2, so we reach minus 180 degrees, right? So that's at infinite. Okay, and where do we reach, and they have the same break frequency, right? Because they're complex conjugate. But where does it happen? Where does it happen for the angles at break frequency? We know that we have 90 degrees. But where does this happen? And I give you a little tip in one of the slides that I gave you. We see a little bit of a hint. You have like these circles drawn onto it.
Will both become 45 degree. And
Look at the sheet that I gave you. There's a hint where it happens. Yeah, you have it in your right hand and you're looking at it right now. Thales' theory helps you a little bit to find out where they add up to 90 degrees.
oh yeah.
It's when you're exactly on this circle.
Yeah.
That's when Thales, right? If you look at does it make sense what I drawn down for you?
Yeah.
You have this, so for the guys in the camera, basically what I'm showing is Thales' theory basically tell us that if you're exactly on these points, and directly on the middle, through the middle point, and these are connected, then whatever you move this point around on the circle, this will always be 90 degrees.
Yeah.
Right? And these two are basically exactly on this. They're building a pair where we know both angles are 90 degrees, and these are, so this would be the theta 1, and this would be theta 2. And since they're exactly the same, or these triangles are exactly the same, they too have to add up to 90 degrees. Okay? So we know this happens, we know this happens exactly at this circle point. We can calculate the circle, and it has a name. It's what we call the natural frequency. Okay? So this we call, or omega n very often referred to. And this is actually also the length of this, right? So it's basically the magnitude or of each pole to the origin. Right? This is our natural frequency. And then we have this portion, or we have this portion here. And we'll look at the angle here. This portion is what? We call this basically the damping portion because our real portion is damping really. And this is cos theta times natural frequency, right?
Yeah.
That's this portion here. And people refer to this as, I think it's a zeta or
Sigma, I think.
I don't know how you call this, but sorry, but times omega n. So this basically is cos theta. Okay? And this is a damping coefficient. It can only be between 0 and 1 or minus 1 and plus 1. In this case, really, it's always positive. And then we also have this point here, which basically, when you project just the imaginary portion of each pole,
Omega exactly.
people call this very often omega d. And omega d basically equals omega n times 1 minus d squared. Okay? Because this is the omega n down here, and you can do the Pythagorean theorem yourself, and you will have this. Okay? So I just wanted you to see all these values, because once you go into Laplace domain and you want to go into tables and whatnot, they will always get it onto they try to build their transfer functions, so they always use these terms here. So that you already know where you want to arrive. And if you see ever that your transfer function is in their format of natural frequencies and these omega d's and these coefficients, you already know what these mean. They're basically tell you how much your damping is, what your natural frequency is, right? So you know where your break frequency is and stuff like that. Okay, this is just to draw this once to you, that you maybe have a little bit of an understanding what all these weird formulas mean. You'll see this once you play around a little bit in discrete math or in Laplace math. These will turn up once in a while. Okay? So they don't really have to throw you off all that much. Okay, so this angle really is what gives us information about the damping. So the length of this tells us how fast this is. How fast is our eigenvalue, right? Or the frequency, the natural frequency. And the angle tells us about damping. So the lower the angle, the more damped the system becomes, right? So if this was lower, it would be also slower, but also better damped. But if you keep in this angle, you can increase the speed, and still the same damping involved. Right? So these are basically the information you can get out of these poles. What's the damping, and how fast are they? Is it a good idea to put these poles here? They're fast and damped. If I put them down here, if I know I have the system, maybe and you will see in Road Locus, I can basically sometimes choose where they are, or that's what we try to do. Is it a good idea to put them really close to the real axis?
Yeah.
The damping is really high, right?
Yeah, it's lower. We try to approach to one that will be more closer to natural frequency. We'll start moving to natural frequency.
So it's also getting slower, obviously, right?
Yeah.
But yeah, play around with this if you want to. And we can actually play around with it, because now maybe we put the camera just over here. We'll just keep it here. A little bit over here. Hopefully this picks it up. Oops. So I did this now for a little bit of an animation. Let's say we put the real portion of to minus 0.3 and the imaginary to 1. So it would basically be like here and here, right? Yeah. And we're looking at the angle. And we'll basically evaluate the same way we did it. We go up here, slowly go up, and get every point and calculate it. And since this is not very well damped, right, the angle is really really steep of these poles, we will see something that we should think that would happen, but maybe we can also describe it together. So now we're past the natural frequency. We're well below 90 degrees, and it slowly goes where we thought, right? The angle goes to slowly to minus 980, and the amplitude also drops, which makes sense, right? Both of them are getting really, really long, and 1 over really, really long is nothing. So that makes a lot of sense. It drops really quickly now. But why did it go up here? What do we call this?
Resonant peak breakdown.
Yes, it's a resonating peak. At our close to our natural frequency, we basically get a resonance. It's because they're not really well damped. And if we now increase the damping, for instance, 1,1, then our angle is 45 degrees. We should see a different behavior. See, this is the magnitude never really went up, right? So we damped it,